Hello class, this is Mr. Matthijs. I'm making a new video for you today, which is going to cover section 3 of chapter 11. It's our game theory chapter. So far in our chapter we've looked at 2x2 matrices representing games with two players and each player has two choices. First we looked at strictly determined choices, where it was pretty easy to find that for each player one of the options was always better than the other option, so the strategy was just to play the better option every single time. And then in the second section we looked at games where that wasn't the case, where you still had two players and two options each, but one of the options was not, you couldn't say that one option was strictly better than the other option, so you came up with some strategy of the optimal distribution among the two options, that you play one of the options some amount of the time, and then the rest of the time you play the other option. So that was strictly determined games and non-strictly determined games. But both of those dealt with 2x2 matrices, games of two players where each player has two options. So in the third section, 11.3 reduction by dominance, we're going to look at games that are not 2x2 matrices. Sometimes you'll have an m by n game matrix, so some arbitrary size bigger than 2x2. And the way that we're going to solve these is to reduce it to a 2x2 matrix. And the way that we can do that is by deleting certain rows and columns. A row can be deleted if there exists another row that will produce better results. And similarly, a column can be deleted if another column can produce better results for the column player. The row or column that produces a better payoff for its corresponding player is said to dominate the row or column for the lesser payoff, right? So if we can find a row that always produces better results than another row, then we can delete the worst row, right? If we can find a column that's always better than another column, we can delete the worst column, right? You would never pick a strategy that's inferior to another strategy. If you have three options and one of the options is always worse than another option, you'll just pick the better option and not the worst option. So by using logic to eliminate inferior choices, we're going to reduce down some larger matrix to a 2x2 matrix. So let's take a look at an example of how this works. Okay, so we've got a game with the game matrix G here. As you can see, it's a 3x3 game. So we have two players with three choices each. And our task is the same as it's always been. For the following game, determine the optimal strategy for both the row player and the column player and find the value of the game. So we're going to use the strategy of dominance. We're going to examine the three rows and see if there's any row that's always worse than any other row, right? So let's compare the rows. Well, look at row 1, -2, 6, 4. Okay, got a few good results there, 6 and 4. -2, not a great result. Look at our second row, -1, -2, -3. Okay, all not good results, all negative results, so that might not be a good option. And then look at our third row, 1, 2, -2. Okay, so it looks like probably the second row is going to be the worst row because they're all negative. But in order to be precise, we need to verify that there's another row that every single column is better than the second row, right? So if we look at the third row, 1 is greater than -1, 2 is greater than -2, and -2 is greater than -3, right? So all the entries in row 3 are better than all the corresponding entries in row 2. So we can say row 3 dominates row 2. So that means there's no reason to ever play the row 2 strategy when you could just play row 3 and be guaranteed a better outcome. So we can eliminate row 2. Therefore, eliminate row 2. Okay, now we can look at our columns and try to do the same thing. The part that's tricky about the columns is that we need to think about what's best for the column player. So it's kind of like the opposite. Remember, all the outcomes are relative to the row player. So what's good for the row player is bad for the column player, and what's bad for the row player is good for the column player, right? So we actually want to pick the column that has the most negative outcomes. If we have higher outcomes, that's actually worse for the column player. So we wouldn't want to pick that one, right? So if we look at our rows, or I mean our columns, right? 6 and 2, those are both positive outcomes and high ones, right? So from the perspective of the column player, this is not a good column. This column is actually dominated by both of the other columns, right? -2 is less than 6 and 1 is less than 2. So from the column player's perspective, column 1 is strictly better than column 2. No matter what, column 1 produces a better outcome than column 2. And what about column 3? Well, 4 is less than 6 and -2 is less than 2. So we can say column 1 and column 3 dominate column 2. Therefore, we will eliminate column 2. So there's no reason why the column player would pick column 2 when they are guaranteed a better result in either the first column or the third column. And again, it's important to remember that when you're picking the column player, you need to think results relative to the column player, meaning that negative numbers are actually better, positive numbers are worse. It's kind of the opposite of the row player's perspective. So what we've just done here is reduce. Now we have what's left, a 2 by 2 matrix with the remaining entries. -2, 4, 1, -2. Okay? So now in order to determine the optimal strategy and the value, now we're ready to just use the techniques that we're very good at after practicing them so much in section 2, right? We're going to start with a arbitrary row strategy, R1 minus R, and see how that does against both columns. So R times -2, -2R. 1 minus R times 1 is 1 minus R. So that'll give us -3R plus 1. And let's see how that does against the second column. 4, -2. So that gives us 4R minus 2 plus 2R, or 6R minus 2. Okay, and then we'll just set these two results equal to each other. And solve for R. So we can add 3R to both sides, and we can add 2 to both sides. Get rid of these. So that'll give us 3 equals 9R. So it looks like R equals 3/9 or 1/3. So that gives us our optimal row strategy. They should play the first choice 1/3 of the time and the second choice 2/3 of the time. So that's the optimal strategy for the row player. Or to be more specific, they should play the first row 1/3 of the time, the second row 0 times ever, 0% of the time, and the third row 2/3 of the time, right? Because we eliminated the second row. So you can either say for the 2 by 2 matrix, it's like this, or you could also say it like this. For the original matrix, 1/3, 0, 2/3. So that's the two ways you can look at the row strategy. Okay, and now we're going to look at the column strategy, right? So we'll pull down our matrix, -2, 4, 1, -2. And we're going to see how that does against an arbitrary column strategy. C1 minus C. So we'll play that against the first row. That'll give us 2 times C, -2C, and 4 times 1 minus C, plus 4 minus 4C, or -6C plus 4. Then we'll play our column strategy against the second row. We get 1 times C is C, -2 times 1 minus C is -2 plus 2C, or 3C minus 2. Okay, so we can just set our two results equal to each other. -6C plus 4 equals 3C minus 2. We can add 6C to both sides, and we can add 2 to both sides. That'll give us 6 equals 9C. So C equals 6 over 9, or 2/3. So it looks like our column strategy should be to play the first choice 2/3 of the time and the second choice 1/3 of the time. And again, that's the column strategy, thinking about our 2 by 2 matrix. In reality, we know that we're going to play the second column 0% of the time. We're never going to play the second column. So you could also consider the column strategy to be like this. 2/3, 0, 1/3. So either way is fine. It's just depending on if you're thinking about our 2 by 2 reduced matrix or our 3 by 3 original matrix, right? So the last task then is to find the value of the game, right? We want to find the value of the game. So we can do. We have kind of two options here, and this is why I showed you both of the ways that we can consider the row and the column optimal strategies. One way you can find the value is by doing your row times our reduced matrix times the column, our 2 by 2 row and our 2 by 2 column. So if we did that, it would look like this. Our 2 by 2 row was 1/3, 2/3. Our reduced matrix, that's this, -2, 4, 1, -2. And our reduced column, our 2 by 2 column, our two choice column, 2/3, 1/3. Right? So if you do this multiplication out, you'll get the value. The other way that you could do it and get the same result would be take our 3 row by the original game by the 3 column, and you should get the same result, and I'll show you why. So our 3 row strategy was 1/3, 0, 2/3. And our original game matrix, 2 6, 4, or negative 2, 6, 4. Negative 1, negative 2, negative 3. And 1, 2, negative 2. And then we have our 3-choice column matrix, 2/3, 0, 1/3. Right? So whether we're doing it with our reduced matrix with the dominated rows and columns removed, or if we do it with our original matrix, just putting in zeros for the dominated row and the dominated column, we're going to get the same result either way, because both of them represent the same thing. Both of them represent that we're not picking the second column and we're not picking the second row. So it's pretty much up to you, whichever way you want to do it. You should get the same result either way. So let's just verify that in our calculator. So I'll go to my calculator. I'll go to matrix. For matrix A, I'll put in our 1x2 row matrix. So that's 1/3, 2/3. Then for matrix B, I'll put in our 2x2 reduced game matrix. -2, 4, 1, -2. And then for matrix C, I'll put in our 2 rows by 1 column column matrix. 2/3, 1/3. So in my calculator, I've done A, B, C. So if I do A times B times C, I should get the value of our gain. A times B times C. And what I get is a value of 0. So it looks like a zero-sum game. If row and column players both play their best strategy, nobody will win or lose. It'll be a wash in the long run. And so then just to verify, let's do the second way of doing it. So I'm going to change matrix A to be a 1x3 matrix with entries 1/3, 0, 2/3. And I'm going to change matrix B to be a 3x3 matrix with entries -2, 6, 4, -1, -2, -3, 1, 2, -2. And I'll change matrix C to be a 3x1 matrix with entries 2/3, 0, and 1/3. And if I've saved those matrices, our new A, our new B, and our new C, if I multiply those, I should get the same result of 0. So let's see if that happens. A times B times C is 0. Right? So this second way of doing it just kind of confirms what we've proved in the first way, that we didn't choose the second row and we didn't choose the second column. So personally, I think that this one is easier. So I would go that way. It's just less buttons to push on the calculator, right? Fewer rows and columns to worry about, but they're both correct, right? Okay, so here, in summary, here's a summary of the section of reduction by dominance. Sometimes an m by n game matrix can be reduced to a 2x2 matrix by deleting dominated rows and columns. A row is called a dominated row if there exists another row that will produce a payoff of equal or better value. That happens when there exists a row whose every entry is larger than the corresponding entry of the dominated row. And a column is called a dominated column if there exists another column that will produce a payoff of equal or better value for the column player. This happens when there exists a column whose every entry is smaller than the corresponding entry of the dominated row, right? So remember, for the row, we want larger results, and for the column, we want smaller results, right? So you just remove dominated rows and columns until you have a 2x2 matrix. Okay, so that pretty much wraps up section 3 of chapter 11. So your homework is to do number 1 through 8, okay? And I'll post this on our class page. I'm going to go ahead, since there was only one example in this section, I'm going to go ahead and do one of the homework questions for you. You're welcome. But if you feel like you got it, you can just move on to the homework right now. Okay, so I wanted to look at number 5 and just see what happens. Because number 5 is a 4x4 matrix, so we're going to need to reduce quite a bit to get to a 2x2. We need to remove 2 rows and 2 columns. So let's look at the rows first. So let's look at the first 2 rows. Is one of these strictly better than the other one? Let's see. 2 is greater than 0. 0 is greater than -6. -4 is greater than -6. And 8 is greater than 2. So every entry in row 1 is better than every corresponding entry in row 2. So we can eliminate row 2. Row 1 dominates row 2. Now let's look at rows 3 and 4, see what happens. Let's compare their entries. Let's see, 2 is better than -2. -4 is greater than -2 is greater than -4. 4 is greater than -8, and 6 is greater than 0. So every entry in the third row is better than every entry in the fourth row. So again, we can say that there's a domination here, that you would never pick the fourth row because the third row is always better. So we can say R3 dominates R4. The third row dominates the fourth row. Okay, now let's look at our 4 columns and see if there's any column that's strictly better than any other column for the column player. And remember, being better for the column player means having lower entries, right? So let's look at the first 2 columns. Okay, 0 is less than 2 and -2 is less than 2. So the second column always is better than the first column for the column player. So we can eliminate the first column. We can say column 2 dominates column 1. And let's see what else we have. Let's look at the third and fourth columns. -4 is less than 8 and 4 is less than 6. So column 3 dominates column 4. Right? You can also look at column 2. 0 is less than 8, -2 is less than 6. So both of these columns dominate column 4. So we won't pick column 4 either. We can say column 4 is dominated. So that gives us our reduced matrix. 0, -4, -2, 4. Okay. So then we can go ahead and find the optimal strategies for both players and find the value of this game by using our 2x2 matrix, where we've reduced by eliminating inferior strategies. So we can go ahead and do that. Why not? So we'll see how an arbitrary row strategy does against the first column. R times 0 is 0. 1 minus r times -2 would give us -2 plus 2r. And against the second column, we would get negative 4r plus 4 minus 4r, negative 8r plus 4. Okay, so let's see what value of r that gives us. Negative 2 plus 2r equals negative 8r plus 4. So I'll add 8r to both sides. And I'll add 2 to both sides. That'll give us 10r equals 6. So r equals 6/10 or 3/5. So our row strategy should be 3/5 and 2/5. Okay. What about our columns? What about our columns? So we'll bring down our matrix. And we'll use an arbitrary column strategy, C, 1 minus C. Play it against the first row. Yeesh. 1 minus C. Okay, 0 times C, 0. Don't even really need to write that. Negative 4 times 1 minus C, negative 4 plus 4C. And we'll play it against the second row. Negative 2 times C, negative 2C. 4 times 1 minus C, plus 4 minus 4C. Or negative 6C plus 4. Okay, so we'll see what value of C that gives us. Negative 4 plus 4C equals negative 6C plus 4. Add 6C to both sides. Add 4 to both sides. That gives us 10C equals 8. Or C equals 8/10 or 4/5. So the column strategy should be 4/5, 1/5. Great. Last but not least, we can find the value, and that's going to be our 2 by 2 row by our reduced matrix by our 2 by 2 column. So our row was 3/5, 2/5. Our reduced matrix was 0, negative 4, negative 2, 4. And our 2 choice column matrix was 4/5, 1/5. So just do that in our calculator. Put in for matrix A, our 1 by 2 row matrix, 3/5, 2/5. For matrix B, I'll put in our 2 by 2 reduced matrix M, 0, negative 4, negative 2, 4. And for C, I'll put in our 2 by 1 column matrix, 4/5 and 1/5. And then A times B times C, A times B times C in our calculator gives us a value of negative 0.8 or negative 4/5. So it looks like a slightly losing game for the row player. even using the best strategy. But that's it. That's how you do it. Okay, so just practice, 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 and have fun. Good luck. If you have any questions, don't hesitate to send me an email. Have a good one. Bye.